We're now going to continue with our understanding of the features of graphs of rational functions. And what we're going to do in this video is we're going to try and understand how to identify a horizontal asymptote. Okay? Now, a vertical asymptote is a place where the values, as we approach a particular x value, the y value gets larger and larger or smaller and smaller. A horizontal asymptote is kind of the inverse of that. A horizontal asymptote is a feature on the graph where as x becomes larger and larger, like as x gets closer to infinity, like as x approaches a million and a billion and a trillion, or negative a million, negative a billion, or negative a trillion, okay, as our x values get very large or very small in either direction, like on a graph, negative infinity to positive infinity, the graph of the function gets closer and closer and closer to one output, okay? And so, a good example of this is, let's say, 5, let's say we have y is equal to 5 over x plus 3. 5 over x plus 3. Well, what happens if we put in a number like 2? If x is equal to 2. When x equals 2, in fact, let's make a graph, or a table here. Let's make a table. When x is equal to, y is equal to. When x is equal to 2, 2 plus 3 is 5, right? And 5 divided by 5 is 1. Well, what if x instead was, let's say, negative 2. Let's say it's negative 2. Negative 2 plus 3 is equal to 1, and 5 divided by 1 is 5, right? These are kind of normal output values. We got the point 2, 1, 2 and 1, negative 2 and 5, negative 2 and 1, 2, 3, 4, 5. So we know that it goes through these 2 points. The y-intercept, if we put a 0 in for x, 0 plus 3 is 3. That's 5 over 3, 5/3, which is basically, it's 1 and 2/3. So here's the y-intercept right here, okay? But what if we put in like 100? Well, if we put 100 in here, 100 plus 3 is 103, and 5 divided by 103, 5 divided by 103 is 0.049. 0.049. What if I put 1,000 in here? Well, 1,000 plus 3, that's 1,003. 5 divided by 1,003 is 0.004, or 0.005. 0.005. What if we put something like 25,000, a really getting kind of big, yeah, it's not that big of a number, but still, 25,000 plus 3 is 25,003. 25. And what's 5 divided by 25,003? 5 divided by 25,003. Okay, that would be 0.0002. 0.0002. What if we just jump ahead and put in 10 million? Put in a really big number. Here's the x-axis, right? Okay, 10 million is way that way. 10 million is off the planet almost. Okay, just keep going. If we plug in 10 million, we'd have 5 divided by 10 million and 3. 5 divided by 10, 1, 2, 3, 1, 2, and then a 3. So 10 million and 3. All right, and that would be 0.0000005. What's happening as our numbers, as our input value gets gigantic, huge? What's happening to this output value? What's this near? What number is this near? Not this one, but these. What are these getting close to? They're getting close to 0. And that'll just keep happening. They'll just get closer and closer and closer to 0. I'll put in 5 divided by 999, 999, 999, 999. And again, this is what I get, okay? I get 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then a 5. Look at that, 0.005. this is even closer to 0. As my numbers get ridiculously large, my output gets closer and closer to 0. Now the same thing would happen if I put in a negative number. Whoops, I didn't put in 999. So this is 999999999, I think it was, something like that. What if I put in negative 1 billion? What I want to show you is that putting in negative numbers does basically the same thing, at least in this case. There are situations where positive numbers make it go to 0 and negative numbers make it go to infinity. Okay, so let's see here. We're going to put in 5 divided by negative 1 billion plus 3. And we get negative. We get basically the same thing as this. Negative 0.00000. I'm probably got the wrong number of zeros here. 5. And negative, this is basically close to negative 0. There is no negative 0, but what that means is that it is approaching 0. The output values are approaching 0 from the bottom of the graph, the bottom of the x-axis. It's getting close to 0, but it's coming up from the bottom, where this is coming from the positive side and going down to 0. That's what a horizontal asymptote is. A horizontal asymptote is a situation where the output value of a graph at very large numbers approaches one output. Okay? And we typically represent it on a graph. We typically represent a horizontal asymptote as a dashed line, a horizontal line that is dashed, and then we draw the graph and make it get really close to the dashed line. That's typically how we represent a horizontal asymptote on a graph. But I'll show you that in the video, in the next set of videos for the next class. Okay, right now we're just learning about the features of rational functions. Okay, well, here's the cool thing about horizontal asymptotes is it's actually very easy to understand how to identify a horizontal asymptote on a rational function. But here's the thing is you have to pay attention. It's so easy that some people overlook it and they think it's complicated, and it's not complicated. All you have to do is look at the power of the numerator versus the power of the denominator. Okay? And here's your rules. There's only 3 possibilities. The first possibility is this. If the numerator power or degree is smaller than the denominator power, then the horizontal asymptote is at y equals 0. The horizontal asymptote is at y equals 0. Why is it y equals? Because horizontal lines are represented by y equals. Look, this is the graph of y equals 2. This is the graph of y equals 5. Okay? When you have y equals a number, that's just a horizontal line. So y equals 0 is a horizontal line at 0. And so here, if the numerator power is smaller than the denominator power, then the horizontal asymptote is always at 0. So here, look at this one. The power of the numerator, this is 7x squared. Now the power is the exponent, not the coefficient. The 7 is larger than the 2, but we're not looking at the coefficient, we're looking at the power. This is x squared, this is x to the 3rd. And so therefore, this function has a horizontal asymptote at y equals 0. This one has a horizontal asymptote at y equals 0. If you were to put a million in here, this 1 million to the 3rd power would be more powerful than 1 million to the 2nd power. You'd have a larger number on the bottom and a smaller number on the top. And when that happens, when you have a larger number, when the bottom is a bigger number than the top, it's approaching 0. Like 1 over 1,000 is really close to 0 because the bottom is a lot bigger than the top. Second rule. If the numerator power is equal to the denominator power the horizontal asymptote is the fraction, that's the top and the bottom, of the lead coefficients. All right, let's look at this situation here. Y equals, we got this over this, right? 6x cubed over 5x cubed. I'm telling you, here's what I'm telling you, is none of this other stuff matters. The only thing that matters is the highest powers. This 2x plus 1 doesn't matter at all. I don't care how, if it could be 1,000,000x plus 1, I don't care. None of that matters. This negative 3x squared plus x, that doesn't matter either. It doesn't matter how many x's, how many extra x's there are, that doesn't matter. The only thing that matters, the only thing, is the highest power x term. And if the highest power x term of the numerator is the same power as the highest power x term of the denominator, then what you're going to do is you're just going to take the fraction of the lead coefficient, 6 over 5. And so, because this has the same power in the numerator and same power in the denominator, this has a horizontal asymptote at y equals 6 over 5. It's just going to be a fraction of the numerator lead coefficient divided by the denominator lead coefficient, 6 over 5. Okay. Lastly, see this one down here? Y equals x to the 5th over 2x to the 3rd. Here, the power in the numerator is larger than the power in the denominator. So here's the deal. That's situation 3. If the numerator power is greater or larger, however you want to say it, than the denominator power, there is no horizontal asymptote. No horizontal asymptote at all. So there's only 2 situations where there's a horizontal asymptote. And that's where the numerator is less powerful or where the numerator is equal powerful. If the numerator is more powerful, there's no horizontal asymptote. However, there could be, when this happens, if the power of the numerator is 1 larger than the denominator, there could be what is called a slant asymptote. In fact, there will be a slant asymptote. We're going to talk about slant asymptotes in the next video. Okay? All right, so let's do a couple examples here. So here, there's no horizontal asymptote. Okay? No horizontal asymptote in this case. There just isn't one. Let's say that we have y is equal to 12x squared plus 9 over 3x to the 5th minus 14. Does this have a horizontal asymptote? Power of the numerator is less than the power of the denominator, so this has a horizontal asymptote at y equals 0. All right, well, let's say that it's x to the 5th, 12x to the 5th plus 9 over 3x to the 5th minus 14. Now, the power of the numerator is equal to the power of the denominator, and the horizontal asymptote is at 12 over 3. So we have a horizontal asymptote at y equals 12 over 3, which is actually 4. So there's a horizontal asymptote at positive 4. Okay? And then if let's say that we had 12x to the 5th over 3x to the 4th, because the power of the numerator is larger than the power of the denominator, this would not have a horizontal asymptote at all, but it would have a slant asymptote. Okay? All right, that's all I have for this. We have one feature of graphs of rational functions left to learn, and that is slant asymptotes. So you're going to have to watch the next video, and you will know everything you need to know about the graphs of, well, the features of the graphs of rational functions.